All right, so we're going to talk about rates of change in tangent lines, which are applications of the limits that we've been studying. So average rate of change, we actually talked about a little bit already, but I want to talk about it with a little bit more difficult example. So let's find the average rate of change of f of x equals x to the third minus x over the interval 1 to 3. So that looks sort of like this. All right, it's a sketch. It's not perfect. It's not beautiful. All right, so at 1, the value is 8. I found this on my calculator. I just typed in the equation, and then I pushed traced, and then I literally just typed 1, enter, and it tells me 8. But you can also get this by plugging in at 3. We're way up here at 24. Okay, so like I said, I did it on my calculator. This point A is 1, 8, and this point B right up here, B, is 3, 24. All right. Now, I want to just talk to you about another way this book especially uses to write points. Sometimes they call it like A for the X value of A, and then F of A for the Y value, because how do you find the Y value? You put A into the function, and so you get out F of A. That is another way to write a point. All right, and the same thing here, it would be like B, F of B. So we're going to use those for our X1, Y1, and X2, Y2. Because remember, average rate of change is just the slope. So, slope for this problem would be 24 minus 8 all over 3 minus 1. In other words, 16 over 2, or 8. That's my average rate of change on that interval. If I draw the line between those 2 points, the slope is 8. All right, so formula for average rate of change is slope. So f of b minus f of a all over b minus a. All right, that is how you find slope. It's the same thing as saying y2 minus y1 over x2 minus x1, but we're going to use the function notation quite a bit for this section and throughout calculus. Now, here's an example of how to find rate of change. Now, if you're AP and you're like, I'm fine with this, I don't need to do this example, move on. That's fine. Okay, so how do I find the rate of change of fruit flies over this 50-day experiment? Experimental biologists often want to know the rates at which populations grow under controlled lab conditions. The graph shows the number of fruit flies grew. All right, so the graph was made by counting fruit flies at regular intervals, plotting points, drawing a smooth curve through the points. So we're going to use the points here at 23,150 and Q at 45,340 in order to calculate the average rate of change over those days. So just the slope. If you want to go ahead and pause and try that yourself, do it. Okay, stop and pause after you look at my answer if you need to like regroup and see what I did. But I want to talk about units. So I got 190 over 22. That's 190 flies, or fruit flies, over 22 days. That's the average rate of change. Now, it might make more sense to round in this case. So 190 divided by 22, I get about 8.6 flies per day. And if you ever have a problem figuring out your units, there they are. If you put them right in your problem along with the numbers that they represent, it should just tell you the units. It's called unit analysis. It's really important. Actually, sometimes I can figure out my mistake by realizing I'm multiplying instead of dividing, or dividing instead of multiplying, just by putting my units on and know what my units are supposed to come out to be. Food for thought. Now, so remember to write the equation of any line. You need a point and you need slope. Okay, so this is definitely review. We've done this already in chapter 1. All right, so if I write an equation of this line through negative 2, 5 with a slope of a half, I'm just going to use point slope form. I don't need to write it in y equals mx plus b form. I'm going to write it in point slope form because that's faster. So y minus 5 equals slope times x minus x1, x plus 2 in this case. So the other thing that we need to remember to do this section is the secant line is a line that intersects the curves in 2 points. All right, so if if I were drawing a secant line on this curve, which looks a lot like our curve that we used for problem number 1, maybe it's more like an x to the third, but it would look like that. So that's a secant line going from P to Q. All right, now, what if we want to know on our fruit fly problem, not fruit fly problem, about the rate of change just on a particular day, like the 23rd day, okay, right here at P. What if I want to know that rate of change? I'm basically asking about the slope right at that point, okay? So we got to talk about tangent lines, but what if we wanted to think about it by starting where we started at Q and then got a little closer? That estimation is a lot closer to the actual value of the slope at that point, and if I got a little closer again, it's a little bit closer, and then if I got a little closer still, that tangent is a little bit, that secant line slope is a little bit closer to the actual value of the rate of change at the 23rd day right there at P. So if I drew the tangent line in, that line from P to B is a lot closer to that value. That's a terrible line. Let me try that again. Of the tangent line right there. And as you see, our slopes are getting closer and closer to the actual slope at that point. So over here's a table that shows what if I go from Q to P? What if I go from 40, 330 to P? What if I go from, so that's the next one, P, X, then Y. So if that's X. Now what if I go from Y to P? And what if I go from B to P? B to P is clearly the best answer, but I'm getting closer and closer to the actual answer. So we're going to talk limits, because closer and closer and closer as we approach P, how can that help us find the actual answer for the slope just right at P? All right, so first we got to talk about tangent lines and what that means, because basically we want to find the slope of a tangent line. So in a circle, a tangent line intersects once. Okay, and it's perpendicular to the radial line. Okay, it's perpendicular to the radius at the point of tangency. On a curve, it's not exactly the same, but it is going to hit the line in just exactly one point, like here, or right here. Now, that's why it's not quite that simple. Right here, it hits the curve locally, like around P, it hits in exactly one point, but it does end up hitting the curve in another point right here. That's okay, but right around P, it is hitting only once. All right, same deal over here, but it actually crosses through the line right there. Okay, that happens sometimes. Tangent lines can cross through the curve at a point of inflection. That is a point where the graph changes from concave up to concave down, and that is one of the things we will answer in calculus, is how to find points of inflection where tangent lines go through the curve. All right, now normal lines. Something that our book talks about a lot. Normal lines are perpendicular to the curve at the point of tangency. All right, now our book uses that tangency. I was missing some letters there. All right, so it's perpendicular. So for instance, this would be the normal line right there. This would be the normal line at P. It's perpendicular. And here's the point right here, perpendicular. Okay, so they're all perpendicular to the curve at the point of tangency. They're also perpendicular to the tangent line at the point of tangency. Okay, so knowing what we know about tangents and knowing what we know about secants, we're going to use that and the idea of limit to find the slope of the tangent line. So here we go. This is really important, so I want you, if you don't understand, to rewind and look again. All right, so this is the concept. We're going to take our point P, and we're going to take a point close to B. We'll call it P. We'll call it Q, and we're going to pretend we can move that closer and closer and closer, like in that fruit fly diagram where we're getting B closer and closer and closer, and we're going to move it so close that possibly it's right on top of it. All right, so let's talk about how we're going to do that. First of all, Our book calls this h. Many books call that delta x. I'm going to have you change it right there to h, but be aware, especially AP, you will see that as delta x sometimes. All right, so how do I find the slope of the secant line? Well, I use the slope formula, right? But let's talk about what this point P is. If this is the value x, it's x comma, and then what's the value here? Well, it's f of x, whatever x is, and you plug it into the equation. All right, so that point is like that. This point over here, now we got x, and this little value is h. So this value over here is whatever x is plus h. So this q is x plus h, comma, put that in, f of x plus h. All right, so that's our point for q. So if I'm finding the slope is equal to y2 minus y1, and they're crazy looking, over x2 minus x1. Now notice what happens right here. That x minus x, they're going to cancel out. So my slope is really going to be f of x plus h minus f of x all over h. Okay, so that is our slope. But so let's talk about how this is a little interesting. What if I moved q a little bit closer and a little bit closer? Like h is only 0.5, and then h is only 0.1, and then h is 0.001, and then h is 0.000001. And what if it's closer and closer and closer to 0? If I make h be smaller and smaller and smaller and smaller and smaller to 0, and it's right on top of each other, what happens? Well, as h is 0, I'm actually getting close to that tangent line. It's not a secant line anymore. So if I find the limit as h goes to 0, I'm actually finding the slope of the tangent line. So the slope of a curve at the point is the slope of the tangent line. And you use the limit as h goes to 0 of the slope formula, this guy right here, to find the slope of the tangent line. So we use limits to find the slope of the tangent line.